Today, we are diving deep. We're going to crack open a seriously dense academic monograph. Now, why would we do that? Well, because hidden inside all this complicated math is a set of tools that could help us tackle some of the biggest problems in quantum mechanics. And, that's the science that's basically building our future. So, here it is, our source material for today. The title is a bit of a mouthful, something like Separability and Spectral Properties of Singular Differential Operators of Mixed Type. Yeah, not exactly light reading, right? This thing is a super specialized text written for mathematicians and physicists who are already way in the weeds on this stuff. And it is laser focused on one very specific, very difficult problem. All right, so how are we going to make sense of this? Here's the game plan. First, we're going to start with the why. What's the problem this math is even trying to solve? Then we'll unpack the basic toolkit of ideas it uses. We'll look at the main strategy. It's a really clever one. See how it all comes together. And then, at the end, we'll zoom out and ask the big question. What does all this mean for us? So first things first, why does a book like this even need to exist? Well, the answer comes from a huge challenge that's sitting right at the heart of a field that fascinates all of us, quantum mechanics. And look, we don't even have to guess why. The book's own introduction lays it out for us, plain and simple. It says that if you want to get real, solid answers in quantum mechanics, you have to get a handle on these things called singular differential operators. They're the mathematical beasts at the very core of how we describe the quantum world. So, what is an operator? You can think of it as a mathematical rule that describes something physical, like the energy of a particle. But here's the catch. In the bizarre world of quantum mechanics, especially when you're talking about huge infinite spaces, these operators become singular. And singular is just a math speak for, hey, this thing is starting to act really weird and unpredictable. Okay, so to wrestle with these wild, unpredictable operators, you can't just jump into the deep end. The book is smart about this. It starts by building a solid foundation, using tools from a field called functional analysis. Let's just quickly define a few key ideas that we're absolutely going to need. First up, the operator itself. This is our main character. And the best way to think about it is like a machine. You put a function in one side, and that function describes the state of a system, and the operator processes it and spits out another function on the other side, maybe one that tells you the system's energy. Input, process, output. Now, these operators aren't just floating around in nothing. They live and work in a very particular environment called a Hilbert space. Honestly, just think of it as the stage where all the weirdness of quantum mechanics plays out. And it has to be an infinite dimensional space, because a tiny quantum particle can be in an infinite number of states at once. You need a space big enough to hold all of those possibilities. All right, next up is the spectrum. This is super cool. Every single operator has a unique set of answers it's allowed to give. Taken all together, these answers form its spectrum. The prism analogy is perfect. You shine white light through a prism and you get a rainbow, the spectrum of light. You analyze an operator and you get its unique spectrum of possible states or answers. It's like its mathematical fingerprint. And this is exactly where the problem starts. See, a spectrum can be discrete, which means you have nice, clean, separate values. Think of steps on a ladder. 1, 2, 3. But the tricky operators in quantum mechanics, they often have a continuous spectrum. It's not a ladder, it's a ramp, a smooth, unbroken smear of possible values. And that, as this book makes very clear, is way harder to analyze. So if these things are so unbelievably complicated, how in the world do you even start to analyze them? Well, the book's first big strategic move, which it lays out in Chapter 4, is a total classic of problem solving. You divide and conquer. I mean, the core idea is something we all get, right? When you're facing a problem that's just too big and overwhelming, you don't try to solve it all at once. You break it down. You find the smaller, more manageable pieces that you can actually solve. In the formal language of this monograph, this whole divide and conquer strategy gets a name: separability. It's the rigorous mathematical process of proving that your big, scary, complex operator, we'll call it A, can be treated as just the sum of its simpler parts, B and C. Proving this is a huge deal because it gives you mathematical permission to use the entire strategy. And this is the process in a nutshell. You start with that messy, mixed-type operator, the one you can't solve. Then you break it down. You deconstruct it into simpler pieces that you actually can analyze. You figure those out one by one, and then you put all those smaller insights back together to finally understand the big picture. It's such an elegant and powerful way to handle a problem that seems totally impossible at first. Okay, so now we've got our basic tools, and we've got this powerful divide and conquer strategy. Now the book can finally guide us toward its main goal, which has been right there in the title all along, to really understand the spectral properties of these operators. In fact, if you just glance at a simplified table of contents, you can see this whole logical journey laid out. Chapters 1 and 2 build the toolkit. Chapter 4 locks in the strategy. And it all builds up to Chapter 6, where all those tools and strategies are finally put to work on the main event. So, here's the key. The book zooms in on this really nasty class of operators called mixed type. Think of them as mathematical chameleons. They can actually change their basic character from something called elliptic, which is kind of like a smooth, closed surface, to hyperbolic, which is more like an open saddle shape. This constant shapeshifting makes them an absolute nightmare to analyze with standard methods. Whew, okay, we have been deep in the mathematical weeds, so let's pull back up and look at the bigger picture. Why does this kind of super abstract, theoretical research actually matter in the real world? Well, work like this is absolutely crucial. It gives us a rock-solid, rigorous mathematical framework for physical problems that used to just fall through the cracks of our standard theories. It invents and proves powerful new methods, like separability, that let us tame these incredibly complex systems. What it's really doing is building a stronger, more reliable foundation for all the math that our entire understanding of the quantum world rests on. And that brings us to the big final question. You think about technologies like quantum computing or really advanced AI. What are they? They're built on our ability to precisely describe, predict, and control unbelievably complex systems. So, while a book like this might feel abstract, it's developing the exact language and the rigorous tools we need to do that. It might not be the blueprint for a quantum computer, but the methods here, taming unpredictable systems by breaking them down into solvable parts, that is precisely the kind of thinking we need. Could this be one of those quiet, unseen stepping stones on the path to truly functional quantum machines? Or maybe even a more stable, predictable AI? It is a pretty fascinating thought.